Hello everybody. Welcome to our seminar today. Today we have actually a longstanding colleague of mine, Mehran Armand, who has been working with me and other members of LCSR. Oh, gee, I don't know. It must be getting on toward maybe, oh, it's over 15 years at least. For many years, Dr. Armand was a member of technical staff, or I don't remember the title, at the Applied Physics Lab. But he's just recently shifted his primary appointment, so he's currently a professor in orthopedic surgery, but he also has significant engineering collaborations with mechanical engineering and us in computer science and in LCSR. And so, Mehran, if you want to say more about yourself as part of your introduction, please do. But it really is a great pleasure to have you here.
Thank you, Ross. Thanks for the introduction. And hello, everyone. It's just a great pleasure to talk to you. And Ross did a good, nice introduction, and I just follow on that. So the topic of the talk here is trends in computer-assisted orthopedic surgery research, as Ross just mentioned. By the way, can you see my screen?
Yeah, your screen is beautiful.
Okay. So I just joined the Department of Orthopedic Surgery, and I think the most appropriate is we focus on the work that I've been doing with collaborative work with Ross, and let's show the collaborators here. And many, definitely close to two decades working with Ross and Peter, and a lot of great collaboration recently with Matthias and Dr. Nawab going on. Also the surgeons from orthopedic surgery, if you see my mouse, the upper right, and then great graduate students from both mechanical engineering and computer science. In fact, this was a good year. We had 4 PhDs that I will going to summarize their work actually in this talk, that we had 4 PhDs graduate, got their PhD this year. And a lot of good students who are continuing to follow their work and the projects we have. The external collaboration is a lot of international collaboration, mainly orthopedic surgeons around the world. And I go through some of the works that they are, we are collaborating with them. So going back to, as Ross said, I started in 2000 at APL. At APL, some of the, besides the medical robotics, that was more collaboration with LCSR at the time, I also focused on some work on what we called unconventional mobility. And that included some, as you're saying, like undulating fins, reconfigurable manipulators, which was work with Dr. Shurikjian, and Bakibot, rolling robot. I don't talk about this too much, but then around 2013, I moved to Hackerman at our lab at Hackerman 135 at LCSR. And ever since, we are continuing to focus on the application of surgical robotics with the collaborators I just mentioned. And the focus here, the system development, as I've shown here, but earlier we started focusing on biomechanical planning for the surgery and intraoperative planning, but that has been extended as I go through it. Now, of course, a lot of this surgical application requires a cadaver lab. We have a lab at Bayview adjacent to the Center of Orthopedic Training, and we perform the studies and all the cadaver studies in that laboratory. And there are some facility for mechanical testing as shown here too. Now the talk today, I focus on 4 areas that I think is exciting as interesting for orthopedic surgery. The biomechanical guidance, that what I started with, and then I add the other 3 areas that I think is really exciting and a lot of potential, and is actually moving forward pretty good in the area of orthopedic surgery. Now, orthopedic surgery is a little bit different from other areas of surgery because you have to deal with hard tissues. And I start with the biomechanical planning to discuss that. One of the example application of how we can use intraoperative biomechanical planning in surgery is hip osteotomy. This is a treatment for hip dysplasia. Now, dysplasia, if it shows here at top left, can you see my cursor in the screen?
Yes, yes.
Okay. So it is also called shallow hip socket. So if you look at hip as ball and socket joints like this, so the ball is not exactly sitting in the socket, and this may be dislocated. And this is usually a disease, well, call it disease for younger females. It occurs in younger females actually. And it's the patient have pains and cannot walk. And if they don't do anything about it, it will change to arthritis later. Now, the surgery that is performed for it is called periacetabular osteotomy, as shown here. It's basically the patient cut part of the cup or part of the acetabulum, which is has the joint on it, and try to rotate that and increase the coverage of the ball or the femoral head. And I see this is a very challenging surgery. They have to maintain this posterior wall there, and at the same time, there's sciatic nerve passing here, and a lot of chiseling is performed. If the surgeon is not very experienced, they may go inside the joint space. That's not a good area. And just this image from Dr. Sobala shows what's happened. And then, of course, they screw the fragment in. So what is done right now, the surgeon basically use a lot of this with eyeballing. The more experienced the surgeon is, the less they use X-ray and use more like haptic or feedback for their touch. But with the X-ray, they try to do. So there's a mental mapping they do where they are with their chisel, with their tool, and they try to perform this. It's very, very challenging. And I think not more than 10 people are in the United States are doing this kind of surgery right now. So this surgery, and another thing about this is, as you see, because with just moving the hip, you're trying to reduce the contact pressure, but there's nothing has been done regarding the biomechanics. This is more like based on some standard anatomical angles. So what we said that if we can create a navigation system that do the biomechanics, do the contact pressure calculation on the hip joint based on some simulation, and also give them some gold standard anatomical angles or data that the surgeons usually use, then we can pretty much put a little bit more science into the surgery done. Original system that we started like very long ago, basically uses optical tracking system. So we attach an optical reference marker on the pelvis, intact part of the pelvis, and we couldn't put anything on the fragment that you want to move around. So we had 3 bare points. We would touch the bare points with the digitizer and try to look at how much the fragment has moved, and then calculate range of motions and other materials. So it worked well. We did some clinical testing with Dr. Lepisto in Finland and Dr. Sobala in Denmark, who did about like 24 cases performed, and they're usually performed. It's a good surgery. I mean, it usually has good outcomes. That has been started for a while. But the problem with using optical tracker is that, as you see, this is a picture from Japan. I think this is Dr. Sugano or Dr. Takao's surgery room. I'm not sure. But as you see that there's a lot of people around, and this is very high impact surgery, a lot of chiseling going on. Optical tracking, the line of sight might not be always available. Plus, like surgeons like Dr. Sobala in Denmark this actually, believe it or not, minimally invasive, only about 7 centimeter opening. He tries to do all those cuts and rotating the pelvis. So the next best thing is if we could come up with a system that instead of using the optical tracker, use the X-ray that is already there and the surgeons are using to perform the surgery. So the whole procedure would be just acquiring a CT scan to creating the 3D model, segment the model, create 3D model of pelvis. Then we use a Halifax BB injector to inject some BBs on the intact part of the pelvis doesn't move, and also some BBs on the part that moves. And this is done before performing the cut on the actuator, but after getting the CT scan. Then so there's some registration, 2D, 3D registration is going on to register the preoperative CT to the X-rays that we are getting through the X-ray with the X-rays. And then once you create a reference from these four, you have a reference rigid body here and reference body on the fragment, and you can track the fragment with respect to with the Fourier green at the time and calculate all the rotations, the anatomical angles that you want, and the contact pressure as needed. So this is the work of Rob Grob, which was our first graduate, is a student of Ross and the first graduate this year. First PhD that we had out of 4, as I mentioned. I'm sorry, I put everything that he did and is published in this Physics and Medicine in one page, which kind of make it very dense. But pretty much as a summary, once you inject the bones, then you reconstruct and recovers relative poses of the C-arm, basically by getting 2 or 3 C-arm. And then for the fragments, fluoroscope for the fragments. So there's one brute force, what you said, trying to find the correspondences between the BBs that you have injected both on pelvis and the acetabulum. And then once you have this, try to do some pruning there and throw away the bones that are very far away and not related here. And then this is done in 2 of the X-rays. Then you project it on the 3rd X-ray view that you have, and then you use the reprojection distances to establish 3 view correspondences there. And after osteotomy, he finds the fragment BBs. Again, this movie played here. The fragment BBs constellation posed by pruning candidates using coarse relative fragment pose prior. So this is what he does basically. And then again, once he gets less number of the candidate poses here, then he computes the reprojection distances and much smallest projection distance. So this is the beauty of this. This is a very fast and automated system, that automated technique that can really be useful for intraoperative surgery and give us the information that we can have. Again, the next work that this is again Rob's work here I'm presenting, it was the fact that again we have to inject BBs, and that's not always the best scenario, especially if you're dealing with pediatric population. So here what we want to do, we attempt to reconstruct, again the same thing, but we try to not to use BBs and do everything image based here. So again, the same procedure, you get the patient CT and you get intraoperative radiographs 2D. And this is something that Rob came up with, which is a 3 multiple object registration, sequential registration. So the intact pelvis, femur, and then the cuts here. The challenge here is all those cuts, because preoperatively, the surgeon can plan the cuts, but usually with all those chiseling, it doesn't mean that whatever those cuts will happen during the surgery. So the fragment shape is sort of unknown to a degree. And that may create differences, that may create difference and create some errors. And again, once having that, we do the projections and the biomechanics and so on. So here again, sorry, this is fiducial, so fiducial based. So here the fiducial is actually our pelvis because it has more details and acts good as a fiducial. And then again, as I said, 3 sequential registration: pelvis, then femur, then the acetabulum. And what Rob looked at is 3 ways of doing to see what are the errors are. One, if we say that we cheat and say we exactly know from the post-operative CT know how the acetabulum looks like. We can just segment that and find it. The second method is we just go with the preoperative plan, whatever the acetabulum look like, then we start use that for our planning and registration. And the third one was trying to look at the x-rays and plan some cuts, find some of the cuts, reproject that on the 3D 3D model and pass planes through them. These cuts not always plane, but create the 3D cuts there. And create the new acetabulum and look at the results. And the results, basically, of course, as predicted, fiducial base works very well. And 2 degrees is pretty good for this surgery. I mean, whatever below 5 degrees is, I consider it really good. And then there is the 3 methods, as I discussed, performed. And as again, if you knew the model, it works very well, actually, as shown here. But even without knowing the model, fiducial, going with the pre-plan or trying to predict the line, the model did acceptable, pretty good job. So this is very promising. The issue is just increasing the speed to the point that we can use it intraoperatively, similar to what fiducial base is done. So that's one example. Another example of including biomechanics, femoral bone augmentation, that I will go through it real fast. Again, this is a fracture of the hip due to the these are osteoporotic hip in elderly, and the fracture rate, the fall is high, and the fracture rate, the mortality after 1 year after the fracture when they fall, it's reported to be up to 60%, which is pretty high. And even after the first fracture, there's a higher chance of the second fracture, and for the second fracture, this rate of mortality exponentially goes higher, more than that. And the preoperative, the preventive measures right now is more like drugs, anti-resorptive drugs, estrogen, and they are very long-term. They don't have short-term effect. And we're talking about the patients who are there in their 80s or older. So a therapeutic approach that can really use was what if, like when the patient fractures the hip, we know the rate of fracture of second hip is very right. If we can somehow augment this bone to make it stronger. And so we came up, as I said, we work on systems usually in the lab. We came up with a system here that has a robot, or it can be a navigation system that injects bone cement, which is usually PMMA. And then there's a C-arm and optical tracker at the same time in the room. So perform the task here. And one important thing is with PMMA, you increase the temperature and you may create bone death. So it is important to plan it well and the injection be very minimized, the amount of bone. At the same time that you want to increase the yield load of the bone and improve the strength of the bone as much as possible. So the plan is include some biomechanical analysis to find how much we are going to strengthen the bone and where would be an entry point and how much we want to inject and how to inject, what the velocity injection and the time of injection there. And here then we have to do some intraoperative analysis too. Again, this is the work of Amir, our very latest graduate this year, Dr. Farvardin, that he just graduated, and he builds on the work of Dr. Bastafa Hassan that previously worked on this. What we start with some finite element of structural optimization to basically fill up the bone with the bone cement and try to reduce it to get to the point that we want is acceptable for us, and the yield is strains are acceptable and the yield load has increased sufficiently, hopefully up to the double or something. And then once we have that, we match it with some we kind of blobs to help us to have single path injection. and with variable dimensions, of course. We find the best trajectory for that. And once we found that, the bone is a porous material, so bone cement will just move through the bone. So we do some hydrodynamic analysis to see that what's the actual trajectory will look like. And the last step is, again, to make sure that you're not creating bone death, necrosis there. We perform heat transfer analysis and see that if that's satisfactory. Again, this was work of Amir. And to do this, again, he showed that we really need, we cannot just go ahead and inject. We have to plan it and come up with some strategy for injection. To do that, we need some sort of use navigation or robotics. So here is the use of early work that done by Dr. Otake here in our lab, that he pretty much used for registration, because once you want to do navigation, you need registration of the bone again to the patient. It is the use of what we call F-track that was attached to the bone. This can recover 3D pose of the X-ray, and we have preoperative CT, of course, and then there's an optical tracker. There's a fixed relationship here. And using this, basically getting the CT, we create the digital radiographs here from the CT data, basically by doing line integration there, and then compare it with the C-arm images, and then with some similarity score, we try to optimize that, and we do the process of registration again. But then the problem was there, again, having just that pin inside the osteoporotic bone, and the range of view of X-ray, that was always problematic. So Kang Gao, our new student in computer science, is basically extending the work actually that Rob did on the femur. And what if we have the kinematics and the tools from the robot's kinematics and the injectors here, and we perform the registration, image-based registration, and we try to perform, find the line of injection from there. And here again, as I said, this is an extension of that, the same thing. We need some initialization, find some original pelvis, and I go through that in a moment to find the registration, perform the registration. And then we use the pelvis because it has a lot of detail as a main fidget shoulder. Once there, after that, the femur will be registered, and the robot tool will be registered, and then we can follow the robot using the kinematic of the robot. Again, this is what's shown here. As you see, first the pelvis, then the femur is registered, and then the robot tool, the injector, is registered to the system. And here you need, again, 3 X-ray views, and with the robot in the plane, so we get 3 X-ray views. You have the tool here in the plane, and then you perform the registration as gone. This is again showing the work on progress that we are doing. We have 2 methods for performing drilling and injection. One is just drill attached here. We are performing the drilling. The other one is guide, that the surgeon performs the drill guides. And then the first method, we have to change the tool, that requires additional registration. And with the second method, you just, the same tool, you just change it, and you put the injector in and inject it. So there no additional registration is needed. So that's a robotic application. It's a work on process that some of the students, including Amir and Mahsan and Kang, are working on it right now. That was one area that I just, I want to go back to the 3 areas that I haven't talked about it. And the other area that is very exciting for orthopedic is tool dexterity, I'm saying. And this is, I'm going to talk about that for first. And yeah, I like this statement here: a good tool improves the way you work, a great tool improves the way you think. And we like to think that having the flexible tools can help the surgeon change the method they are doing the surgery, the approach they are using toward performing some of those surgical tasks. again, this is the work when compared to soft tissue surgery and hard tissue surgery, you will see that over the years, the flexibility of the tools for soft tissue have drastically improved. Autonomy and not as much because it's more challenging to deal with autonomy for soft tissues, but dexterity has really gone a long way. For orthopedic application, actually, the first application, RoboDoc, that Peter Ross was, of course, part of it. So main part of that. So it started with and continues with it was kind of autonomous, performing most of the tasks, many of the tasks automatically, but the tools were all rigid. The tools for orthopedics continue to stay rigid tools because you have to deal with hard bone, you need the stiffness and stability there. But here, so I'm going to another example here to show. This is treatment of osteolysis. So here what happens, the liner, this is after total hip replacement when the cup is in place as shown here. This polyliner here, polyethylene liner, gets some erosion and that creates some bone inflammation and osteolysis behind the hip. Now, you don't want to remove the cup after doing the hip revision surgery possible because that may produce fracture. So what the surgeons do, get the screws all up and go through the screw holes and try to clean the osteolysis and feed it with bone fragment and with bone fragments and bone cement as much as possible. The issue here is they can hardly reach all the osteolytic bone behind the cup. This the literature reports up to 50% is usually cleaned. So here we say, what if we can use flexible tools to go and increase that reach? The goal here to increase the reach and clean up as much as possible. So again, this is a manipulator that I'm going to show about and the way we want to treat this problem. Again, there is a system here. There's a robot, a manipulator, and snake-like manipulator attached to it with optical tracker and sense and C-arm in place. So we want to pretty much go through the screw hole, but we go with a flexible tool, continuum manipulator. That's flexible tools pass through it to do the cleaning and debriding. So this is the continuum manipulator that will attach to the 60-degree of freedom robot. It's cable driven. You pull the cable, the manipulator bends, but it bends in one plane to give it stability. The other part of it is the tools that have to pass there. They have to have flexible stem, a range of tools that we were working on it. This is the work started with Dr. Alam Beji that graduated at Shahriar, Dr. Sefati that just graduated this year, continued now Justin Ma, another student of ours is working on it. Again, of course, having this with a robot, you need some mechanism for feedback and real-time feedback. The work that's been done in our lab with collaboration with Dr. Yurdo Chita, it's developing fiber Bragg rating sensors that passes through the walls of the manipulator, continuum manipulator. And these sensors can give us like the shape of the manipulator and the position of the tip of a manipulator as the surgery is performed. And of course, a driver that will attach to the robot can drive the robot and tools for us. So again, we start, as I said, this is the manipulator that over the years, we started with this manipulator, which was 2 nitinol tubes attached to each other. They're cable driven and only planar articulation. But then that, and this is the typical cup that you see the screw holes, 6.6 millimeter. So this is a 6 millimeter manipulating passing through it and the liner is removed. And this is a newer version that we've been working on it that makes from 1 rod instead of making it 2 pipes. So make it manufacturing much easier. And the holes here basically is the cable channels, the pull cable channels, and also the sensor channels, the FPG sensor channels that can be used to detect for the thing. So this is a movie of showing the snake as you pull the cables moving and rotating. And the tools, of course, all have flexible stems here, as shown here. So they have to be able to cut hard bone, and also so for soft tissues we have for debriding we have some tools, and we have to have sufficient torque transmission, and this is a typical uh, shape of the tool that tool with the flexible torque coil that we are using for this. And again, the work of Shahryar and Justin Ma shows that it's really, these tools really work well, and actually even in straight cutting, they really don't change the speed of cutting that much for us cutting and milling. And these are the type of tools that used in this procedure. And I guess I showed this movie before. This is with the tool inside. This is a simulated bone. This is the work of Farshid, Dr. Alambeji, that showed this cutting through the simulated bone. We can go on a curve path and perform the task. We are having an infrared camera that is just showing the trajectory there. And of course, all this done, again, we have to perform a control here. So we have a feedback, we have sensory feedback, and we have X-ray, and we can perform some sort of combinatory control of the robot. Here, that's based on system kinematics and Jacobian. So the snake moves inside an environment that is ever changing. So the Jacobian of the robot, as it deals with different obstacles and environment, that estimate, we can have a model, but that estimate has to change. So we need a system for updating the Jacobian. This is the work of Shahryar, again, performed, presented in IRAS. So moreover, you need to do combined control of the snake and the manipulator. There are several constraints that you have to apply. We have to make sure that you pass through the school hub, so you have sort of remote center of motion here. There is a space limitation, so you want to make sure that the body of the snake is within a cone and it doesn't hit the cup or hit the body of the patient. And at the same time, you want to get maximum reachability for the snake. So again, we calculated where the tip of the snake is, where the snake wants to go, and you send the command, you generate command, which is the command wants to, again, subject to several constraints. At the same time, you want to minimize the joint movement, the big joint movements of the robot, and as much as possible, maximize the movement of the snake. And so these ratings can help to do that. And once the command is sent, of course, as you deal with the environment, the Jacobian has to be updated. So the relationship between the tip and the robot, the tip movement and the cable length, that relationship is not fixed and it keeps moving. And as you say, so there's a second optimization process going on that is updates the Jacobian for us relatively, minimize the Jacobian for us. So again, this is one application that this is what Shahryar and Rachel Hickman, that she's left right now, the lab, they perform the task and showing that the planning with the snake going through the screw holes on a simulated bone and reaching all the waypoints that they want to reach with the system, with the combined control. Again, going for the next few slides, I have some cadaver that some people may not like the images. So you can not watch for a few slides and I will tell you when you can watch again if you don't like to watch cadavers. This is the same task performed on a cadaver. As you see, the snake is going through the screw hole and try to reach different points within the cadaver. Again, we have this opening here so we can visualize it. In reality, that's not an opening. And this is performed, and this is again the same thing, but this time there's a milling flexible milling that's going, and they're trying to cut a simulated bone within the screw holes, satisfying all the constraints that exist in the procedure for performing this task. And this is interesting in the sense that you can see that as Nick passes, it can bend almost 180 degrees within the joint, after the joint. So again, this has other applications, and other applications that is pretty much interesting is core decompression, removing the dead bone. Usually this is done with a straight tool, but right now some of our students, Justin Ma and my son, are working on it to extend the work that Shahriar started, Dr. Safadi started, to perform curve drilling. And so that will bring us exactly where the dead bone is rather than going on the straight path, and allow us to remove all the dead bone rather than some of it again. Again, once you have a curved path, you need something to go through it. This is the paper that Dr. Alan Beji published, and this is a screw that can be flexed as a self-tapping bending screw that can go through that curved path for us, and then we can reinforce with bone cement and other or bone graft as needed. Showing this tool, this would be a useful tool. We feel that this might be useful for things like pelvis fracture, for trauma, when you really don't have that much room and you don't have a straight path. Having these kind of screws might be useful for that kind of applications. Now I talk about a little bit data-driven models here. So the three type of data-driven models, I think this is a really exciting area that is going to really affect and improve the field of orthopedic surgery as well. So the offline learning, then for medical images, also for robot sensors, I will go to back to the FPG there, and then some recurrent learning for robot manipulation. So I talked about three type of data-driven models that we'll be using. Again, this work, this is Dr. Umberat's work, actually, that he was the brain behind it. And as I said in registry, for annotation of the points is very important, both in radiological aspect for it and also for initialization when you're performing registration. Here, what's happening basically, the surgeon is this is an example of using deep learning for interventional radiology, and it's basically you use the X-ray images, you have a CT images, you create, you annotate some points, and then you create realistic X-rays from it, and several stages of it, and then try to annotate some point and train a network on the X-rays. And this is like the digitally radiographs that the work of Dr. Umbrat that make those realistic radiographs as goes through. And then this network predicts belief maps for 23 landmarks in single X-ray structures based on convolutional pose machine used for estimation of human pose from RGB images. Estimation of the belief map is performed in 6 stages. First stage, as shown here, the 6 stages. The first stage estimates based on local image features only. Subsequent stages improve the estimate of and incorporate of improve those the first the features there, and gives more basically long-term contextual dependency between the landmarks here. So again, it's using the model is good. That's a great, but a lot of time the model itself may not have may not be as good as using the X-rays itself for training, X-ray images itself. And especially because there's a lot of time, a lot of tools, screws, retractors, okay, wires here in the model that you haven't have it in model, you have it on X-ray images. And then if you can use original X-ray for making the training, that might really improve the performance of the network or deep learning network. So again, there's this is again a work of Rob. He has like 1,000 real images and CTs of the cadaver experiments. But the problem is annotation of all those images is hard. So how we can annotate the X-ray images and use that for training. This is this is a paradigm he came up with. I'm not going through the whole paradigm here, but Rob worked on a global optimization method here that combines the differential evolution, particle swarm, exhaustive search, CMA, and barbecue. So he has barbecue. So he has all these methods and tries to perform a good registration, a good lengthy registration on what they have to the images, the X-ray based on the X-ray images. And once it does some of those, and visually you can see which one are good, and the ones that are not good, you can just discard them basically. Once you have that good registration there for that, then you can use that as basis of applying a unit there and perform the training. And basically what you want to do, you want to do the labeling of the objects, segments there, and also the develop heat maps for the landmarks. So here is one of the results that's shown here. As you see that these results are pretty good actually. You can see that the cross and the circles are pretty close to each other. And again, this can be a great way of starting the initialization of the registration and also finding those annotations. And then again, I just go toward another application for this would be like pretty much using the FPG sensors here. We have the sensors, and one of the problems here to calibrate the sensors beforehand, it takes a long time. So what we want to do here as much as possible is to, so this is a work of Shahriar Safati again. He basically has a camera here. Instead of calibrating the snake with the sensors preoperatively, he moves the sensor under a camera during the surgery, during the operation, and create a model, use machine learning to create a model of that, and then try to predict if the model has a collision or not with an obstacle there in the line. So this is preoperative. You have a training data, you have a machine learning model that it develops it, and then that detects the collision and tells you the probability of the collision with some signification that if you're hitting an obstacle or not, pretty much. Again, this is FPG in practice. Again, I didn't talk about it, 3 nitinals that have 3 sensors on each of it, and it is within a nitinol rod here and pass through these nitinol scales. As you see here, as they hit different obstacles with different stiffness properties, they respond to it based on the probability analysis. And so the third, again, this is the work of Dr. Al-Ambejri here. Some of the work that we do for online data training here, use of real-time data for updating the snake's performance in the given environment. So here we're using 2 examples, one for soft tissue manipulation. The algorithm discovers the camera, the algorithm that he uses here. Let me just compare these 2. It's basically you look at cameras, it finds the camera's intrinsic and extrinsic properties. And what it's trying to do, he tried to match the 2 green points to the red points here. And this is done by the robot using the optimization algorithm, and this is done by the human. As you see, the robot actually performed the task much better. This is a heterogeneous soft tissue, like simulating soft tissue material, heterogeneous material here. The same concept can you use it for robot interaction with material. Basically, robot interacts with material obstacles. He has a plan points that he wants to reach there. By interaction, he learns the properties and he adjusts his Jacobian and he moves toward that point successfully. And he tried it with several different materials as shown here. So this is a third example of how we can use data-driven models for our orthopedic applications or our control. Now, the last part that is really, I think, is very exciting for orthopedics, and many orthopedic surgeons are very excited about it, is the visualization part. This is, again, the part that was fortunate working with Dr. Nawab here, collaborating with him, and established a lot of applications that, based on augmented reality, that is very useful. Now, this is a lot of this work is work of Jawad, which is our second to last PhD graduate this year. And I'm just going to present some of his great work that he has done here. So the general issue here is, and I may go 5 minutes over time, Ross, if that's okay. So
well, you do need to try to leave people time for questions, and
okay, sure,
people you'll lose, but
okay.
But you've got theoretically till noon.
Okay, and it takes 5 more minutes to go through this. We have, so basically, as I said, like this pelvis, sacroiliac joint or superior superior pubic ramus, like fractures. Again, that's flat bone, and the thing is, you have so much little real estate here to send the K-wire in or reduce the fracture, and that's may cause multiple trial and errors during the surgery. So the use of augmented reality would be really helpful. That was one example. Another example that is shown here, I jumped to a hip replacement. Again, for hip replacement, placing the cup with good anteversion and abduction angles is very important. And so here, augmented reality is used and the study was done with, I guess, 8 orthopedic surgery training, try to use a couple of x-rays and a planned trajectory to be able to perform this cup placement. And it was shown that, so they have the metrics they measured was time, surgical task load, system usability, that they saw significant improvement on that. The radiation dosage didn't change that much. Maybe they were not using that much radiation here. They don't use that much x-rays. So this is one example of how augmented reality can really help boost orthopedics. Then again, the general vision here is, right now, most of the surgery is performed here at top right. You see the surgeons are looking at the surgical scene, but x-rays are somewhere else. They have to do the mental mapping here. What we are moving and what the visualization that will really help if you perform mixed reality. So this is again work of Dr. Nawab with CAMC, camera augmented C-arm, that you can see also do see inside and outside and perform the tracking, or the use of augmented reality and hot mounted display that you can overlay the x-rays right on where the surgical scene is, and so you have a better feel of what's going on, and you don't have to it gives you a lot more control over what you are doing here. Again, this is the work of Jawad, that the 3 if he asked, the surgeon could observe all the x-ray images where they acquired. The crew could also observe all the floating imagery data, and the training surgeons could review all acquisitions together. And he came up with the idea of having these frustums with augmented, with head-mounted displays, that he can use basically that frustum, create that frustum and move the images, x-ray images within the frustum from the source to detector for the scaling, and also put it on the where it's one has to be to look at how to better give a better feel to the surgeon. Again, so here, there's a camera mounted, there's a head mounted display mounted on the C-arm looking at the world, one with the surgeon or the crew, they can have a crew. And then what you want to find here is you have the frustum, the image geometry, and then you want to find this relationship between source and CR, the head-mounted display, and the word and the head-mounted display, and visualize a frustum. Again, this has major several applications. This is one of the things that one application shown that the surgeon picks the thing based on the different positions of C-arm and shows it on exactly where it's supposed to be or where he wants to see that. Then this is another good example for the unmotorized C-arm. The frustums can help you, guide you to go back to the original position. And many times you will get the X-ray in position, you go to another position with your C-arm, and then you want to go back to the original position or a closed back position. So this would be really useful for that. And then again, the work of so orthopedic is one area. The other area that we are focusing is craniofacial surgery. I don't cover that basically single stage. This is what happens. The surgeon has a bigger implant usually after the brain, so they don't know exact the size of the cut, and then it tries to make it to the right size during the surgery. And as what the Joshua Liu and Weilen Hong working on this application is they have a file, they build a 5-axis laser machine as shown. Previously, the surgeon does that all manually, which is very error prone and sometimes takes up to 80 minutes to perform that. So they're coming up with the strategy using the basically camera to look at the area during the surgery and then project the size of the actual planned implant on the head, and all use the 5-axis to send the data to the 5-axis machine to cut it. Now, the application we are showing actually is the milling, because these implants can be used to put other equipment so there's a real estate there that you can put equipment for electrodes for epilepsy, or basically use it as a place that you put your pumps for drug delivery there within the implant. So that will bring me to the end. As you said, this is thankful to having great graduate students to work in both Department of Mechanical Engineering and computer science, and many great collaborators. Thank you.
Okay.
I'm ready for questions.
Sure, we do have some time for questions. In fact, you've done very well in that regard. There's one question in the chat. Quote, wouldn't that tool be great for oncological bone procedures? And I'm not sure which tool was mentioned. I suspect it was the snake drill. Do you want to talk about that at all?
Yeah, I'm trying to bring the chat. Sorry, to make sure I see the chat.
Well, that's the question. I just read it.
Okay. Yeah, actually, when we started, we had the oncology on the basically in mind.
That was the original motivation, in fact, as I recall. And then
yeah, that was the original motivation there. In a sense, it was harder because they use a lot of plates and a lot of other things there. So we decided that with the osteolysis, that might be like a more compact application to start with. But that's a very good question. Oncology is actually a great application that this can be extended to that. And we hope to, in the future, we start working on that.
Okay, Dr. Fischlinger waved his hand.
Hi,
mostly we don't
nice to meet you.
Waving hands, so you need to do is just sing out. But go ahead.
Yeah, hey Mehran, it's fantastic, and it's so great to see you online. I have tons of questions. Maybe I should go in reverse order. You showed that milling machine and the one-stop shopping. is there an intraoperative sterilization for the thing that you cut out? The cranioplasty piece that you want to put in, it has to be sterilized in the OR, right?
The machine, well, so yeah, but the machine would be like separate from this. So what we are doing to get the cut is non-touch. So that doesn't need the sterilization. So it's like any optical imaging, again, the projection and cut. But once we get the data, there's a sterilized implant in the machine there, and the machine, that area is sterilized, but it is it's not exactly close to the bed, surgical bed. But the implant, yes, is sterilized, and laser cuts it, so it's hopefully it's a non-touch cut, so it still stays sterilized there, and you're just applying heat, so it should be okay. That was that your question?
Yeah, you showed the bone drill on the snake. What's the RPM on that bone drill? Is it like a wheat chopper or?
Oh, we are going up to 6,000 RPM right now.
Wow.
Yeah.
That's
yeah.
And,
I mean, that's the work
other,
of Justin Ma. Is actually characterizing it right now, and it's going up to 6,000 Ma.
Yeah. The other thing that I thought that what if you make it more compliant and just use it as a wheat chopper, so that you might get away with less control, the requirements for less control if you make it yeah, this is really like a wheat chopper from softer material.
So that would help us to reduce the RPM.
I don't know, but if you think about, for example, vertebroplasty application,
but
the need for drilling is a lot less than for debriefing.
Okay, so one of the things that I try to show, so what we've been trying to do with the tool, with the snake, is to create several tools and be able to change the tools pretty much using the snake. So we use the snake as a guide for us, that we pass the tools through it. Okay. So you can either bring the snake out, change the tool. Change the tool should be easy. There is a snap-on tool. Now there's issues with sterilization, of course. We have to be careful about that. Or if the tool is small enough that can pass through the inner cannula of the snake, we can just pull the tool out and move another tool inside. So yeah, we can have a series of tools. One of the things that we had work on the curette, that is a small curette that can basically be expanded. We have work, I didn't show that one before. And both milling and drilling tools. And we had a shaver that I guess I showed it on the picture. If I share the screen again. So there's several tools that we're trying to use for it. But the drilling and milling for what our application is the main thing right now, which is osteonecrosis. So
I see.
That's
is there any possibility for vertebroplasty where the big, so to speak,
it's good that you're talking about it.
Guys, this is a CS audience. I've noticed that we're using a lot of medical terms, which
okay.
I know what they are.
Sorry.
But it's like sailing, okay? Vertebroplasty is a procedure where you're basically putting a drill or a big needle down one of the struts that connects the front part of your spine to the back part, and then injecting cement into it. And it's the drilling is a little like drilling down, say, your little finger without missing the bone, without going out of the bone. Okay. So go ahead. And what was your question?
Well, actually, it's funny you said, because one of the applications that we are working is actually, it's not vertebroplasty, but it's a spine decompression, basically.
Yeah,
going and cleaning up the disc.
I'm part of it. One thing, Gabor, folks, this is primarily a CS seminar. What do you see as the biggest computing or image analysis challenges? I mean, we have systems, we have real-time software, we have, but where do you see the real bottlenecks and research opportunities in terms of computer science are? Mehran?
The question, I'm sorry, can you repeat the question?
Okay, the question is really, this is a computer science audience. And
the
in
images.
addition to the devices, which are sort of key enablers, the information that you use to figure out what the device is to do, and then the ways to control the device and so forth are very much computer science questions, especially when they get into medical imaging and machine learning.
Mhm.
Could you say a little more about those, the challenges moving forward in those sort of problems? I mean, we talk about it a lot, of course, in the research meetings, but perhaps people would be interested to hear that.
So again, in relation to robotics, you mean, basically, not the whole area of imaging or thing, or
well, whatever. I mean, to the things you've been talking about.
okay.
I mean,
So yeah, again, two areas that I pinpointed that are very important, where I'm very actually, I think it's very exciting to work on, is the area of machine learning and basic data-driven models that will be used both in robotics, robotic application. I give an example of for sensors, that how we can use, rather than doing a pre-op calibration, how we can use real-time calibration using machine learning for sensors and calibrate our sensors and use it in surgical scenario in relatively fast time. Or the other application, or imaging, as I said, that the issue of annotation, finding those anatomical landmarks that on X-rays, and pretty much initialization, as it is important for every registration application. Those are, I think those are that area, the challenges, there's still way to go. There's things that we haven't addressed. Having like tools in the surgical, every image that you see has multiple tools and multiple things in it that has to be included when we do all these training and learning applications using machine learning. So those are the areas that I think can take some research energy, work on it. The other areas that the whole area of augmented reality and combining that with robotics, I think that would be, my sense is augmented reality is great. It doesn't have an accuracy, but it gives some, if you can perform even the application with robotics, using the augmented reality or that visualization, you can, in parallel, do some sanity check what the robot is doing, pretty much. You have a good visualization, see the interior structures, and have a better feel of what the robot's doing and going. So it's like extra eyes that you have on the application. So it works in parallel, and it works with robotics at the same time. So I think application, improving the visualization is one great area that I see that would be very useful in robotics. Again, the whole issue of controls, improving the controls, but dealing with both soft tissue and hard tissues, that would be, again, requires more algorithmic development and takes some research energy. There's a great deal of work done in that area, but I still think it has room to go forward.
Are there other questions from the audience? I had one other, but okay, and I don't know if I cut Gabor off, but the other question I had is, where do you see in these robot assisted or computer assisted orthopedic interventions, is there a role for autonomy, and what sort of autonomous systems do you see having a role in the moderate to near future in these sort of applications?
Well, my feeling is you have a better chance to see autonomy moving forward in orthopedics more than other surgical applications. That's because bone is harder to cut and maneuver through, but it's more predictable than soft tissues. So making that thing making the procedures more automated, I think orthopedic is a great place to start.
Sure.
And to move forward on that.
Well, in fact, I did start there with the robot hip surgery 30 years ago. But moving forward, if once we get out of machining bone into more interactive procedures or things where the decisions are made in the operating room, how would you see that going? What after sort of preparing bone for hip implants, or what would you see? What are the kind of autonomies that we might begin to see beyond using the robot as a milling machine?
Okay, yeah, well, that's a good question. So I think we want to have always surgeon in the loop, pretty much. So that we want to have. So perhaps we want to think about autonomy in the context of having the surgeon in the loop, but also helping the surgeon to make decisions, helping the surgeon to make better decisions, or helping to analyze the decisions that he's making with a system that works with the surgeon pretty much.
Okay. Okay. Well, are there any other questions that people have? Gabor, did I cut you off? I thought you maybe had one other, and then we're running low on time. But...
Oh, I asked my most burning questions.
Okay.
Okay.
Okay. Well, go ahead. Anyone? Okay. Well, if we're done, then I think we should all thank our speaker. Like I said at the beginning, Mehran has been just and remains, continues, and will in the future be an amazing collaborator. Personally, I see us having to do these sorts of things, to build these human-machine partnerships, to do surgery better. It really, you need teams where people also begin to almost contribute to out of their own field. And I think this is a good example of that. In any case, if there are no other questions, why don't I stop the recording? And I think we should all thank our speaker very much. Give him virtual applause or real applause, or you can also send money. He will take that. Okay.
Well, thank you everyone for joining the conference.
Okay.
Okay.